Alright, so here the question is based on kernel regression with a polynomial kernel, and in fact we are also given the polynomial kernel. It's a polynomial kernel of degree 2, okay? And it says it's applied on the following dataset with two features. So this is the dataset X, and X is a 2 by 3 matrix, so which means uh, the feature space is R2, right? And there are three data points, okay? And we are also given the corresponding Y. Now it says the weight vector can be written as W equal to phi x times alpha, where phi is the transformation mapping corresponding to the kernel, and the vector alpha is given by k inverse of y. Okay, so alpha is equal to k inverse of y. The first question asks us to compute k, right, which is known as the kernel matrix. So what is k? K is nothing but it's a 3. First of all, it's a 3 by 3 matrix. Why 3 by 3? Because 3 is the number of data points that we have. Okay, so it's going to be a 3 by 3 matrix. And what is the ijth entry of k? So ijth entry means ith row and jth column. So that is going to be the kernel function applied on xi and xj, right? Which is nothing but 1 plus xi transpose xj whole square. Now, a quick thing to observe is that uh, since the kernel function applied on xi xj will be same as the kernel function applied on xj comma xi, right? So we can say that kij will be equal to kji, which means that the matrix K that we require is a symmetric matrix. It is a symmetric matrix. Okay, so now this is all we know, and now let's start to compute the each entry, ijth entry of K. So K11 would be nothing but 1 plus x1 transpose x1 whole square. So now this particular value is equal to 1. So K11 is equal to 4. Similarly, we can compute K12 as 1 plus x1 transpose x2 whole square. Now notice that x1 transpose x2 is going to be equal to 0. So this essentially we have 1 square, which is nothing but 1. Similarly, we can compute K13 to be 1 plus x1 transpose x3 whole square, which is again equal to 1. Now observe one thing, that x1 is nothing but the first feature, which is the first column in x, x2 is the second column, and x3 is the third column respectively. Also, one more thing to be observed is that K12 is same as K21, right? Because we have already shown that K is a symmetric matrix, and similarly K13 is same as K31. So now we have to compute K23, K22, and K33, because again K23 will be nothing but K32, right? So now let's compute each of these values. So after computing these, we will obtain that uh, K11 and K22 are 4, and all other values are equal to 1. So now let's write the matrix K, which is nothing but K equals to, we have 4 uh, 4 and 1 on the diagonal, and everything else is 1, right? So this is the matrix K that we require. In the second question, we are asked to find a prediction for the data point 1 comma minus 1 transpose, right? So now in order to find the prediction, what we have to do is we have to, so what is the prediction like? So prediction is given by W transpose phi of x test or xt, where what is xt here? Xt is nothing but the vector 1 comma minus 1. Now we are already given that W can be written as phi x multiplied with alpha, right? So in place of W, if I replace W by phi x times alpha, I will get alpha transpose times phi of capital X multiplied, the transpose of this multiplied with phi of xt. Now that is equal to alpha transpose, right? And this phi x transpose is nothing but a matrix whose first row is phi of x1 and the last row is phi of x3 because we have 3 data points, right? And phi xt is again a column vector, right? So now you observe, apart from alpha t, the other values are nothing but k of x1 comma xt, k of x2 comma xt, and k of x3 comma xt, right? So let's first compute k of x1 comma xt, x2 comma xt, and x3 comma xt first. So what would be k of x1 comma xt? It is nothing but, as given in the question, 1 plus x1 transpose. So x1 is 1 0 transpose with xt. Xt is 1 minus 1, right? And then we take the whole square. Now this turns out to be 1 plus 1 whole square, which is equal to 4. Similarly, if I compute k of x2 comma xt, that would be equal to 1 plus 0 1 multiplied by 1 minus 1, and then again whole squared. This will be equal to 1 minus 1 whole square, which is equal to 0. Similarly, we can compute k of x3 comma xt, which would be nothing but 1 plus, again x3 is 0 0 multiplied with 1 1, and then the whole square, which leads us to 1 square, which is equal to 1, right? So we've obtained these values. So the prediction that we require can be written as alpha transpose multiplied with 4 0 and 1. Now we need to compute alpha. So how do we compute alpha? Alpha is nothing but, it's given to be k inverse of y, k inverse times y. Now the computationally intense thing is to find the inverse of k. So this is a very important question because anyone who doesn't know how to find inverse of a matrix will definitely lose a lot of marks. So how do we find the inverse of any matrix? So first of all, we'll start with writing k and the identity matrix as a single matrix. So k is nothing but 4 1 1 1 4 1 1 1 1. So this along with 1 0 0 0 1 0 and 0 0 1. We will start with this matrix, right? And then we will perform row operations so that the left hand side vector or the left hand side matrix becomes the identity matrix. And then we will observe that whatever we have on the right hand side is nothing but the inverse that we require. Alright, so to find the inverse of this particular matrix, the first step should be to make this particular entry equal to 1. For that, we have to multiply the first row by 4. So now the top left entry is our pivot entry. So the next step should be to make all other entries in the first column to be equal to 0. That is, the entry in the second row first column and the third row first column, that should be equal to 0. So what we have to do is we have to replace R2 by R2 minus R1, and we have to replace R3 by R3 minus R1. So after doing that, the next pivot entry would be the element at entry 2 comma 2, which is nothing but 15 by 4. So we essentially multiply the second row by 4 by 15 in order to make it 1. So now that we have made the element at 2 comma 2 to be equal to 1, now we have to make the element at row 1 column 2 and row 3 column 2 to be equal to 0, which is the 1 by 4 above 1 and the 3 by 4 below 1, that should be converted to 0. So in order to do that, we have to apply some row transformations. So for that, we have to apply, or we have to replace R1 by R1 minus 1/4 of R2, and R3 has to be replaced by R3 minus 3/4 of R2. So after doing that, our next pivot would be the element at 3 comma 3, which is 3 by 5. So the next operation should be multiplying the third row by 5 by 3 in order to make that 1. And after that, we will have to reduce the 1 by 5, which is above 3 by 5. That should also be converted to 0. So our next step of operations would be in the following order. First, we have to reduce R3 into R3 times 5 by 3, and then R1 will be replaced by R1 minus R3 by 5, and R2 will be replaced by R2 minus R3 by 5. So I would encourage everyone to do these operations by hand, and then we can obtain the matrix form as follows. So now on the left hand side we have the identity matrix, which is 3 by 3, and whatever we have on the right hand side is nothing but the inverse of k. So now let's recall that alpha is nothing but k inverse multiplied by y, which is the inverse of k, which we have obtained earlier, multiplied with y, and y is also given to us in the question, which is nothing but 2, 1 and 2. Now doing the matrix multiplication, we can obtain 0, minus 1 by 3 and 7 by 3. Now recall again that the prediction that we require is nothing but alpha transpose 401. Now we can put the value of alpha that we have obtained into this. So that will be 0 minus 1 by 3, 7 by 3 multiplied with 401, which is nothing but 7 by 3, which is 2.33. So this is the final answer. Alright, so this is the second question. So we have a binary classification data set with 2000 data points belonging to 0, 1, 2. So what does this mean? This means that all of them are binary features. Okay, so binary features. Okay, and again it's also said that it's a binary classification data set. And how many features are there? There are 2 features, f1 and f2, right? So that's why we have 0, 1 square, right? So this denotes the number of features. Okay, so it says what is the estimated value of f2 equal to 0 given y is equal to 1. So now this is nothing but equal to 1 minus the probability of f2 is equal to 1 given y is equal to 1. Now observe that this is already given to be 0.05, so it would be 1 minus 0.05, which is equal to 0.95. So the next question says, what will be the predicted label for the data point 1, 0? So what does this mean? This means that f1 is 1 and f2 is equal to 0, right? So we need to compute essentially 2 values. First is the probability that y is equal to 1 given f1 is 1 and f2 is 0. We also need to compute the probability that y is equal to 0 given f1 is equal to 1 and f2 is equal to 0, right? Now, so the idea is that the first probability will be proportional to probability f1 is equal to 1, f2 is equal to 0 given y equal to 1 multiplied with the probability that y is equal to 1. See, this is obtained using Bayes theorem. Now we will also have probability f1 equal to 1, f2 equal to 0 in the denominator, but we are ignoring it. Why? Because that is a value which we will also have in the denominator of the second probability, right? So since they are same, they cannot be used in comparison, and also there is no direct method to evaluate it, right? Okay, so the second probability would be proportional to probability f1 is equal to 1, f2 is equal to 0 given y is equal to 0 multiplied with the probability that y is equal to 0, right? Now whichever is higher, that label will be assigned to the data point 1, 0. Okay, so let me expand this to be equal to probability f1 is equal to 1 given y is equal to 1 multiplied with the probability that f2 is equal to 0 given y is equal to 1. Now remember that we are able to do this because of the very critical assumption of naive Bayes, which says that the features are independent given the class value, right? So it's also called class conditional independence of features. Okay. So we need to essentially multiply this with this and this. So that would be equal to, so all of these values or all of these estimates are provided. So probability f1 is equal to 1 given y is equal to 1 is given here to be 0.15. So this would be 0.15 multiplied with probability f2 is 0 given y is equal to 1. So we know the value that probability f2 is 1 given y is equal to 1. So we can obtain the probability that f2 is 0 given y is equal to 1 to be equal to 1 minus 0.05, right, which will be 0.95. So that second term would be 0.95. And then we also have the probability that y is equal to 1, which is given to us to be 0.4. Now let me compute the value. So on computation, the value turns out to be 0.057. Now let's do the same thing for the second probability. So in the second case, we can again expand this to be using the class conditional assumption. Probability f1 is equal to 1 given y is equal to 0 multiplied with the probability that f2 is equal to 0 given y is equal to 0, right? So again, we need to compute or we need to multiply three probabilities. The first one is probability f1 is equal to 1 given y equal to 0, which is given to us to be 0.25, right? So it would be 0.25 multiplied with. Next we have f2 is equal to 0 given y is equal to 0, right? Now that would be obtained from here, right? So probability f2 is equal to 0 given y equal to 0 is nothing but 1 minus 0.35, which is equal to 0.65. So 0.25 will be multiplied by 0.65 and probability y equal to 0 would be nothing but 0.6. How is it 0.6? Again, we have obtained that using here. From here we can say probability y equal to 0 would be 1 minus 0.4, 0.4, which is equal to 0.6, right? So now again we have to compute the product of these three probabilities. So let me compute that. So on computation, the value turns out to be 0.0975. So obviously the second value is bigger than the first value, right? So the second label, which is the label 0, will be assigned to this data point. So the assigned label is equal to 0, right? So this is the final answer. So the next question is based on KNN, K nearest neighbors, right? So we are given 5 data points along with the labels and the feature space is R3, right? Now it says that we are using a KNN algorithm with K is equal to 3 and they have given a test point. Now we have to find what would be the label which is assigned to this test point. Now let's, before diving into this question, let's discuss few ideas about KNN. So how do we find the predicate label for a new data point? As a first step, we have to compute the distance between xi and xt, where xt is the new data point and xi, I running from 1 to 5, are the data points in the training data set. So we need to compute the difference between the norms. So the difference between the vector norm squared, okay? Or it's also the distance squared. And then we have to look at the labels of the closest 3 data points and assign the majority label. So at this point, I would suggest everyone to pause the video and find out the distance between xt, x1 and so on up to xt, x5 on your own, right? And then come back and look at the answers. So now we can see that the smallest 3 distances are 2, 6 and 5 respectively, which corresponds to the points x1, x3 and x4, right? So now observe the label corresponding to x1 is 0, the label corresponding to x3 is 1 and the label corresponding to x4 is also 0, which means we have the labels 0, 1 and 0. So out of this the majority is 0, right? So 0 will be assigned to the assigned label to x test. So we can say that y test hat is equal to 0. This is the final answer. Alright, so here we have the question. Suppose you want to use a naive based classifier to predict whether a student will pass or fail an exam, right? So what is the outcome? So the outcome is that, so let me call that, so probability y is equal to 1, which stands for the probability that the student will pass, and y equal to 0 stands for the student will fail, right? So we need to estimate this probability, which is typically denoted by p hat, okay, or p1 hat, whatever. So that is one part of it. And it says it's based on two features, okay? So there are two features. The first one is the number of hours they studied, right? And the second one is whether they attended review sessions, okay? So observe that the second feature, which is whether they attended review sessions, this is a binary feature, okay? So this particular feature is binary, whereas the first one is not binary, okay? So we have, let me call the second feature f2. So we have to estimate the probability that f2 is equal to 1 given y is equal to 1, right? Because the moment we do this, we will automatically get the probability that f2 is equal to 0 given y equal to 1, right? That can be easily obtained by doing 1 minus of this, right? Similarly, we also have to obtain the probability that f2 is equal to 1 given y equal to 0. So these are typically denoted as p11 hat and p01 hat, okay? So these are the notations, okay? So so there are three parameters which we have to estimate as of now. Now we are yet to look at the first feature, right? So the first feature is the number of hours they studied. So again, the number of hours they studied, given that the student has passed, which is given y equal to 1, this will follow some distribution, right? Which is again not specified, but it will have some mean, right? Say, let me call that mu1, and it will have some variance, right? Now let me call that sigma square. Again, similarly, n given y equal to 0, which means the number of hours student has studied given that they have failed, that will also follow a similar distribution where mean will be mu2 and the variance will be again sigma square. Why will the variance be sigma square? It is given that the variances of the study hours of the study hour distributions are equal for both the categories, right? So now observe that we have three parameters here that we have to estimate, right? And we have two here, which is a total of 5, and then observe that these parameters are the same, right? So in total we have 6 parameters that we have to estimate. So 6 is the final answer. Okay, so here we have the question. Consider the following regression model. Yi given xi is equal to w transpose xi plus epsilon I, where epsilon follows normal 0, 1. Now the question says for some lambda positive, where lambda is a real number, the mean squared error of w hat ml is greater than the mean squared error of w hat ridge. So let's first try to recall what w hat ml and w hat ridge are. So w hat ml is nothing but xx transpose whole inverse xy, and w hat ridge is xx transpose plus lambda I whole inverse xy. So there is an additional plus lambda I term here, right? So from here we can say that the mean squared error of w hat ml is nothing but equal to the expectation of the normed difference between w hat ml and w, which is the original parameter value, which we do not know the hypothetical value. So now this difference would be equal to sigma square multiplied with the trace of xx transpose whole inverse, right? So this essentially means, so what does trace of this mean? It means we are actually summing up the eigenvalues of 1 by lambda I, right? Where lambda I is an eigenvalue of xx transpose inverse, or sorry, xx transpose, okay? So since lambda I is an eigenvalue of xx transpose, 1 by lambda I will be an eigenvalue of xx transpose whole inverse. and the summation will be nothing but the trace, because the trace of any matrix is nothing but the sum of its eigenvalues, right? So the same thing we can write, the mean squared error of W hat ridge would be equal to, again, the expected normed difference between W hat ridge and W, which would be equal to sigma square multiplied by the trace of, so here I would have XX transpose plus lambda I whole inverse, right? So essentially this would be equal to the sum of some numbers where each of them are of the form 1 by lambda I plus lambda, right? Because what would be the eigenvalue of XX transpose plus lambda I? It would be lambda I plus lambda, right? So lambda I plus lambda is an eigenvalue of XX transpose plus lambda I, right? So now we can see that since we have increased the denominator, right, that means we have reduced the mean squared error, right? So this implies that since lambda, so there is some lambda which is a real number, and this lambda is definitely positive, because if it's negative then we will be reducing the denominator, right? So since lambda is positive, we have increased the denominator, right? Which means the MSE of W hat ridge would be less than the MSE of W hat ML. And this is exactly what is asked in the question, right? So the answer is actually true. Now, if you want a detailed explanation of how the MSE is equal to sigma square times the trace of XX transpose inverse, you have to let me know down in the comments below. I'll make a detailed proof on that along with the intuitive explanation. So in the second part of the question, we are asked to consider the Bayesian formulation of the linear regression problem, right? Where the prior for W is assumed to be Laplace 0, 2 by lambda. So also we are given the Laplace distribution function, right? So what is that equal to? So what would be f of W? That would be 1 by 2b, which is nothing but lambda by 4 multiplied by e to the power minus of, so x minus mu mod, that would be nothing but mod of W, right? Because mu is 0, right? So that would be mod of W. And then we have 1 by B, which will be nothing but lambda by 2, right? So this would be the distribution function of W, or this is, so this is also known as the prior, okay? So this is also known as the prior. So the question actually asks us to find out the value of, or find out the map estimate of W, right? Which is nothing but maximum a posteriori. Now what does that mean? That means we have to find the posterior distribution and try to maximize it. So we know that the posterior is nothing but the likelihood multiplied with the prior. So now the likelihood can be written as the product of the PDF of standard normal distribution. Now observe that we have written the standard normal distribution, but in the power of the exponent e, we have written W transpose xi minus yi. Now what does that mean? So this is nothing but actually equal to epsilon I, right? So so observe that in the original equation we have yi equal to W transpose xi plus epsilon, right? So epsilon I is nothing but yi minus W transpose xi, or equivalently, since we are taking square, it doesn't matter. So we can say it's nothing but W transpose xi minus yi whole square. Now, since this is a product, we can actually consider the product as e to the power minus, and then we can take the sum of all W transpose xi's, right? Because essentially we have that e to the power a into e to the power b will be nothing but e to the power a plus b. So now we have taken that as a summation, but again, on the outer side, we have 1 by under root 2 pi whole to the power n, right? Because it is being multiplied n times. Again, one more thing to observe is that why are we able to take the product of the PDFs? That is because we are assuming that xi's, or all the epsilon i's are independent, right? Also, it is not explicitly mentioned that they are independent, but in a linear regression problem, the noise or epsilon I is actually assumed to be IID random variables, right? So IID means identical and independent distributed, right? So they are independent. Since they are independent, we are able to take the product of the PDF as the joint PDF. Now coming back to the problem, we have to multiply the likelihood with the prior, which means that we have to multiply it by lambda by 4 into e to the power minus lambda by 2 multiplied with norm of W. Also, this norm is norm 1, right? Or we can also write this as just mod W, okay? So it's the same thing. Now, map estimate asks us to maximize this particular value, right? So this means you have to maximize. So this implies that you have to maximize the negative of summation W transpose xi minus yi whole square, right? Minus lambda by 2 and then mod of W or norm 1 of W, okay? So since we have to maximize this, that implies that is same as minimize summation W transpose xi minus yi whole square plus lambda by 2 multiplied by mod of W. Also, one more thing to be noted is that so there should be a by 2 here, okay? Right, because, so what is the PDF of the standard normal distribution? So the PDF of fz is equal, so if z follows standard normal, that means the PDF of z is 1 by under root 2 pi multiplied with e to the power minus z square by 2. So I previously missed out the 2 here, so this would be minus half, right? And then there will be a half here. So this is same as minimize summation W transpose xi minus yi whole square plus lambda times norm of W, right? And this is actually the final answer. So this is what, so whatever W we obtained by minimizing this value, that is our map estimate or W hat map. So here we have a straightforward question on entropy. It says, suppose we have a binary classification problem in which a decision tree is classifying data points into two classes A and B in a particular node of a tree. So we have a node, okay, it's a big node. Out of this, 60% of the data points belong to class A. So 0.6, they are all belonging to class A, and 0.4 of them are belonging to class B, right? Now to compute the entropy, so the entropy is given by minus P log P minus 1 minus P log of 1 minus P. Again, observe that we are taking log base 2, okay? So that will be equal to minus 0.6 times log base 2 of 0.6 minus 0.4 times log base 2 of 0.4. Now, when you compute, this would be equal to, now this turns out to be equal to 0.9709. So this is the final answer. So this is the entropy. And there's also a question which says, do you have enough information to find the entropy of this node? Yeah, of course, we just did find the entropy. Alright, so here again we have a question on linear regression. So we're given the loss function. So from this loss function, we know that the optimal weight vector W star is obtained as follows. We obtain it as XX transpose whole inverse multiplied with X times Y, right? So this is the weight vector that we obtain after minimizing the loss function, okay? So now we have to investigate what would happen to W star if the value of yi is doubled, right? And also when the value of xi's are doubled, okay? So that is what we have to investigate. So now let us replace, in place of 2y, let's in place of y, let's write 2y, right? So that would be W star, let me write 2 is equal to xx transpose whole inverse multiplied by x times 2y, right? Now this is nothing but 2 times of xx transpose whole inverse x times y, right? Which is nothing but 2 times of w star, right? So when we doubled the y vector, right, the optimal weight vector also got doubled. So we can say that if we double all the values of yi, w star will also get doubled. Now let's try to double all the features by replacing x by 2x, right? So let me call that, say, w3 star. That is equal to, so instead of x I'll write 2x, so that would be 2x times 2x whole transpose, and then an inverse, and then we have 2x multiplied by y, right? So now that will be equal to 4 times xx transpose, and this whole thing will be inverse multiplied by 2xy. Now since this is an inverse, 4 will come out as 1 by 4, right? So I'll have 1 by 4 multiplied by xx transpose whole inverse times 2 times xy. Now this 2 and 4 will get cancelled, so I'll have half of w star, right? So essentially we saw that when we double all the values of xi, w star will get halved. So the first and the third option are correct. So here we have a question in which we have to select the true options, okay? So obviously the first option is true because in any decision tree we choose a particular split if the information gain corresponding to that split is greater than the information gain for any other split. Okay, so a split is nothing but a question, right? So a question is better if the information gain is higher. Okay, that is true. So the first option is actually correct. In fact, I have discussed this in detail in a previous video. Now in the second option we have that the training dataset is not required while predicting the label of a test point. Now this is false. Why is this false? Because we just saw in another question that we require the entire training dataset in order to predict the label of a test point, right? Because we have to compute the distance between the new point and every other point in the training dataset. The third option is also false because it says that a question of the form fk less than equal to theta always partitions the data set into two non-empty sets. Now, it could be the case that one of them is empty, okay? So it could be the case that one of them means one of those partitions is empty. So it is possible. So this is again not true. The fourth option says the depth of the tree is a hyperparameter and has to be chosen using cross-validation. So again, the depth of a tree is a hyperparameter. This is true, right? And we usually choose it using cross-validation. This is also a fact. It has also been discussed extensively in a previous video. Now the last option says decision trees are prone to underfit if the maximum depth is too low. Now this is again a relative question because whether it will underfit or overfit. So this depends on the data. Okay, so this depends on the data set, right? Because for example, let me take a simple example. Let's take the example of linear regression. Okay, so in linear regression, when will we have an underfit? We will have an underfit when the data set, the original data, is non-linear, right? If the original data is non-linear, we'll have an underfit because in linear regression, we assume linearity, right? We assume, something of the form y is equal to ax plus b, right? So since we assume this, and when the data is non-linear, we have an underfit, right? So similarly, decision tree will have an underfit if there are maybe like a lot of patterns in the data, right? But if there is a simple pattern which can be described by only one depth or by only one question, then it will not underfit, okay? But what is correct is that decision tree will have a low bias, okay? So let me write that down. So decision trees typically are low bias, high variance model. Okay. Now I will explain bias variance trade-off and how to determine if an algorithm has low or high bias and all that. Again, if you require such a video, then let me know down in the comments down below. Okay. Okay. So this is what typically a decision tree is. Okay. But the moment you restrict the decision tree to have depth 1, right, you are allowing the bias to be high, right? So decision tree with max depth. So max depth is the parameter that you use in Python, right? So max depth is equal to 1, then the bias can be high. Okay, the bias can be high. Understand that the bias is actually an inherent property of the model. It doesn't depend on the data set, right? But whether it underfits or overfits, that depends on the data set. So typically what happens is that many machine learning engineers make this common mistake of associating bias with underfit. So they think that high bias means it will be an underfit and low bias means it will be, not an underfit. But that is not the case, okay? Because the moment you use the word underfit or overfit, that depends on the data set. But we can definitely say that decision tree will have high bias when you restrict it to a maximum depth of 1, right? So this is actually a dicey option. So the answer would be the actual answer would be that it depends on the data set, right? If the data set is so according to the data set, it will be an underfit or an overfit, or it can be a normal fit as well. All right. So here we have a question which says that we have a data set of only 3 points, right? And we are assuming a leave one out cross validation. Now, what does that mean? That means you will remove one data point and apply the model on the other 2 data points, right? And the model is assumed to be a linear model, W0 plus W1x, right? So suppose W is obtained when 2 is left out, okay? So 2 is used in the validation left data point. That means this is left out in training. Okay, so in training we will only use the data points 1 2 and 0 1. Okay, so dt would be equal to 1 comma 2 and 0 comma 1. Right, now we have to fit a line to this. Right, now the crazy thing about this question is that you don't have to compute w as like so typically we compute W1 as the covariance of xy divided by the variance of x, right? So this is typically what we do. But in this question, since there is only 2 points, the fit would be the line joining these 2 points. The line joining these 2 points. So what will that be? So we can write that as y equal to mx plus c, where m is the slope and c is the intercept. So what is m? M would be 2 minus 1 divided by 1 minus 0, which is equal to 1. And c would be equal to, see, when we put, so 0 comma 1 is a data point. That means when x is 0, y is equal to 1. That means c is equal to 1. So I can write this as y is equal to x plus 1. So this is the fit. Okay, so this is the line which is fitting. So from here we can say that w0 is 1 and w1 is also 1, right? So in that case, what will be the norm square of w? The norm square of w will be w0 square plus w1 square, which is equal to 1 plus 1, which is equal to 2. So the answer is